All right, we might make a start. Hi, everyone. Oh, hello. So today we are very lucky to be joined by Jordan Pierce. And Jordan Pierce is an interdisciplinary scientist specialising in software and AI-driven tools for marine ecology. I've known about Jordan since I very first started my PhD. I think the first paper I ever read was a paper written by Jordan. So I've been following his research for many, many years. A lot of my own work builds on the work that he did. So I can't believe it's actually the first time that I'm technically meeting you, Jordan, so nice to meet you. But I'm really excited to hear this seminar today and hope you all are too. So without any further ado, I might hand it over to you now, Jordan. So we have about an hour for the whole session, but hopefully that'll have some time for questions as well. So thank you very much. Awesome. And can we all make Jordan feel welcome, please?
Thanks, everybody. I appreciate it. Yeah, and likewise, Scarlett. I'll bring your paper up actually in this. Hey, everyone. As was said, my name's Jordan Pierce. I'm a marine data scientist and also a student. I'll get to that in a second. But the title of the talk, as you can see, is from in-situ to in-silico, a brief history of computer vision and coral reef ecology. Kind of gonna hop straight into it. So my background's kind of a mix, actually. So I have a bachelor's in GIS and geography and some work in oceanography from Texas A&M. I had a 2-year stint in Asia where I spent part of my time as a research assistant at HKU, or Hong Kong University. And that's kind of where I got involved in coral reef ecology. I went to CCOM, Center for Coastal and Ocean Mapping, to do my master's in oceanography, but with a really heavy emphasis in computer vision, particularly for coral reef ecology. And then from there, I actually worked in industry for about 2 years at a startup called TerraDepth, and then for NOAA here in the States for about 4 years. And actually right now, I am a Ph.D. student at UCSD in the computer science department underneath Falko Kuester, working with Stuart Sandon as well. So. And I'm actually currently finishing up trying to, at least my first chapter, which is more focused on image annotation, a software called CoralNet Toolbox. It's not a good name. I'm very aware of that because CoralNet has a completely different name, which we'll see in a second. But this is sort of a panoptic segmentation tool for images and orthomosaics, mostly catered towards ecologists and people who are working in the benthic, but it's pretty domain agnostic. It's got a lot of AI-assisted or fully automated tools, which can help with image annotation. But I'm actually not going to spend like any time talking about that at all. If you're interested, we can talk later, or you can just find it on GitHub. But today's talk, I'm actually going to be talking, it's more like a literature review. And we kind of have like this core thesis of the talk. So that like for a while, like in the beginning, computer vision in reef ecology was sort of treated as like isolated classification contests, and we'll talk about that in a bit. So like there were some interesting algorithms, but the real breakthroughs didn't actually happen until these tools were actually integrated into these existing monitoring workflows. And if you want to walk away from the talk right now, that's the key takeaway message. If you want ecologists to use what you're creating, you need to meet them where they're at. So as we go through this, we'll sort of see where these shifts sort of come about and where they lead to. And usually it's where integration comes to sort of meet with everyday ecological practices. It's not necessarily just better AI models, although that does have a big play to it. And we're actually going to track this evolution through 2 parallel stories. The first is sort of the shift in 2D annotation, and then also the recovery of 3D structure and geometry. So starting out, before we talk about computer vision, we actually have to remember where reef monitoring actually started. And this is sort of in the pre-imagery era where everything just happened underwater. You had to identify species and count them and actually physically measure the reef structure, all while fighting, the clock, how much air you had in your tank, how much bottom time you actually had, which is, sometimes limited based on where you're at. And once you surfaced, the visual context is completely gone, right? The only thing that you actually have are your field notes, which, when you're creating field notes at the time, they seem like really good. And then you surface and you're like, what was I thinking? So this kind of created a massive bottleneck, as you can imagine. And crucially, from sort of a academic perspective, there wasn't really a permanent visual record to go back to. So if someone questioned your data or your thesis, you kind of just had to trust them. And that's kind of a big issue. Not only that, but there's also a time where like methods were a bit more invasive. For example, measuring structural complexity, which we'll talk about a little bit later. But even with these like severe underwater constraints, this early period was obviously critical because it helped establish the sort of foundational metrics for the entire field that we still use today. During this time, they weren't attempting to build complete contiguous maps of the reef, which is something that we're kind of doing a little bit more now. That comes later on, obviously. Instead, they actually relied on sparse points or line samples to really generate just statistical summaries, most notably percent cover, which you'll see that the whole first half is just about points. And this is a really important detail to keep in mind because when computer vision does enter the picture, it doesn't immediately try to invent new ecological metrics. Instead, like the first successful algorithms were actually designed specifically to just replicate what the sort of legacy point count methods already did. And here's a really good image of that. If you look at the bottom, you can kind of see that we have, this is like a literal instrument that you would kind of place on the seafloor, and there's a grid of dots on there, and it's kind of akin to like coral point count, but you would basically kind of drop this pin through it, and you would see where that pin lands on it, and you could randomize like where you place this pin. So, you know, there's a little bit of randomness in there for statistics. So why change the system if experts had already sort of like, they could already do this on the reef? Obviously, the advantage was that if you're a trained biologist, you can make high taxonomical calls right there on the spot. You don't need software, you don't have to wait. But obviously, there was a huge trade-off. Like your data was entirely kept on how much air you had in your tank. And obviously, accuracy tends to drop if you're a diver and you start getting tired or the visibility worsens. If you've been scuba diving, you'll see where you're at, like the conditions change while you're down there sort of actively. And most importantly, if two experts sort of like disagree, there's no objective visual record to go back to and audit, right? So the lack of permanence and scalability is kind of what pushed towards the new field or the next part of the field, which is using images, that as well as having the technology to actually have underwater camera housing. So by introducing photo quadrats and video surveys, they were able to completely sort of decouple data collection from the interpretation. So instead of burning precious bottle time, trying to just like identify what the species is right there in front of you, which could take time, divers could just capture, you know, hundreds, maybe even thousands of like high resolution images, and then they could just bring it back to their lab. And this, for the first time, was like it's kind of like the first easy way of creating permanent audible archives that experts could then review years later, even today. And without really knowing it, and obviously this wasn't the purpose of it, but they were actually building these sort of large image data sets that help lay the groundwork for the future that computer vision would sort of depend on whenever it did arrive. But an important note to make here is that what didn't change when cameras were first introduced. So ecologists essentially took their old in-situ techniques and then sort of like mapped them back onto the digital photograph. So you can see here in this image with PhotoQuad. So the foundational unit of analysis was still this idea of a sample point. It's not really the entire image. We're not painting the image to create contiguous maps. And while photography essentially solved the previous underwater time limits, it did in fact trigger, you know, you could say like the beginning of a massive data explosion that we're still dealing with now. So suddenly teams had thousands of images and human experts couldn't like, you know, just keep pace. And sure, you have tools like PhotoQuad or CPCE, which is coral point counts with Excel extensions, but they really just help standardize the workflow. The real main sort of bottleneck was kind of just moving the diver from underwater and placing them inside the lab at the chair. They still have a lot of data to go through. There's not really a form of automation at this point. And as researchers process more images, a new problem emerged, which didn't really exist at this scale beforehand, is again, humans didn't really, some human experts didn't always agree. So, think about it, like disagreement becomes a sort of measurable factor. And software like CPC and PhotoQuad, again, they sort of help standardize the point count annotation methodology across different labs. and they successfully sort of professionalized the workflow, but didn't solve the core issue. Experts were still having to look at every single point in the image, which created a massive bottleneck. This bottleneck, but in turn, is actually what set the stage for the first wave of computer vision. I have a really small bladder, so if I get to go to the bathroom, I might actually. Yeah. So personally, I don't think that early computer vision algorithms necessarily developed to address the scale of images that were being collected back then. Personally, I think it's rather that like they were developed as a result of having the imagery in the first place. Imagine all of a sudden you have all of these images coming in of coral reefs, and you're like, oh, let's do something with it, rather than like the other way around. But of course, these early systems didn't really see the reef the same way that humans do, nor do they now. Not really. We're still trying to get there. But instead, they looked at these like tiny isolated patches. Not this image, the next one, heavily relying on these sort of handcrafted color and texture features. And because they lacked broader context, these techniques were, you could say, like fairly brittle, and they mostly remained as sort of like technical lab demonstrations, like incremental progress, but nothing that could be scaled, not yet. But they were still historically vital because they actually proved that reef imagery contained enough stable data to make automation like a plausible, realistic goal. They actually contained some signal that computer vision algorithms could potentially learn. But before modern deep learning, algorithms couldn't actually, figure out what a coral looked like given this massive amount of data. Nowadays, you literally have supervised learning, or even in some cases, self-supervised or unsupervised. You just give it like a buttload of data and it'll learn from it. Instead, researchers used handcrafted features. If you're familiar with those, I'll talk about it in a second. They, in this case, mostly we're looking at texture. So there's examples of different handcrafted features that were sort of ported over from the main domain of computer vision to coral reef ecology, but a common one that was often used in this context was local binary patterns. And when I first started doing my master's, I remember reading like a bunch of different variations of local binary patterns. You'll see them in images, you'll see them sometimes in topography as well. If you're working with rosters representing, like 2.5D DEMs. But essentially, you would take like these 3x3 windows of pixels, and you would compare their pixel or their brightness, sorry, and generate sort of this like binary code. And then you could pool all of these codes together to create a histogram. And that histogram is like sort of a mathematical fingerprint of like that particular area, or maybe that part of the reef or that particular coral. And that histogram actually served as the feature vector that they would then train their model on. And this is sort of where we get to like the first, like most important part, I think, of the story is moving to, his name's Oscar Baybaum. I don't know if that's how you pronounce his name, but he's a really cool dude. He had a couple of great papers, but in 2012 and 2015, he sort of laid down the foundation for CoralNet, which was fundamentally a texture classification system. And he and his team sort of recognized that downward facing 2D images of reefs and reef classes often lack clean edges. If you look at coral images, there's a lot of fuzzy boundary in between those two. And more often than not, it's more of texture rather than, it's more of like stuff rather than things, which is like real terminology in computer vision. One major highlight of how they tried to address this patch dilemma that other folks were working with was they found that obviously a large patch might be heterogeneous, and that you have multiple class categories within this individual patch, which you can see up here in these top 4 images. This is useful, but again, you kind of have like this mixed signal of class categories within this one patch. But if you have a really small patch, then you actually might have too little information within it, and you wouldn't actually be able to train a model on it. So their solution is to sort of combine the feature vectors that they would get from multiple patch windows and sort of concatenate them together. And then in their work, they found that this actually provided some pretty good results. I wouldn't say this necessarily solved the problem. Patches are notorious for being sort of like a fickle form of annotation, but they do have their uses. And they also introduced this idea of using lab color space for their images. So instead of, working with other underwater color correction techniques, they used this, which helped kind of prove how reliable it was at looking at images across years. And I would say that the most important thing from Oscar's work was that it kind of put this idea of like operation into context or into focus. They didn't just test on a single benchmark data set. They actually tested moving across different years to prove that their technique, their algorithm could actually handle these natural shifts that occur in the environment. Because, between 1 year, 2 years, 3 years, they kind of change substantially. And, which was great because they actually took this benchmark data set and actually made it publicly available for other folks as well. The big benefit to this is you start to bring in folks in the wider computer vision world, which is a good thing. It's something that we should still be focusing on today. There's a lot of experts who are working in different domains, and if we're sort of gatekeeping, or there's this sort of hurdle that keeps them from entering in this domain just because of a lack of data, like that's something that we should kind of focus on, making sure that our data is not siloed. Sorry, over the place. The most important thing is that they actually proved that they could show with automation, they could actually do reliably calculate, estimate coral cover. And more importantly is how they actually did so. When they did this form of automation, they made sure that it aligned perfectly with the exact data outputs that ecologists and their monitoring systems were already using and what they expected. This is how you actually get folks to adopt your techniques, is you meet them where they're at instead of trying to introduce something entirely new and have them shift from where they're currently at to what you're doing. And in most cases, in some situations, it's such a dramatic shift, but it's also really useful that they're worth changing what they're doing entirely. They also touched on something that was something else that was extremely important, and that was how they evaluated success. So when it comes to algorithms and computer vision, instead of holding a machine sort of to this impossible standard of having 100% accuracy, what they actually did is they measured the variance between human experts. So they had a couple of human experts, and they pointed out that even the humans disagreed with each other on difficult categories. And they called this the sort of human envelope. And they proved that as long as you had an automated technique, as long as the machine's estimates fell within that natural human variance, then you could consider that the tool was, ecologically valid. Like it's just like any other expert. Instead of trying to assume that it needs to be 100% to be useful, it just needs to be good enough. And you also need to be able to measure that variance, measure that error. Sorry. And this is sort of crucial because it actually is what allowed for the shift of being just like a single research project and actually be able to scale up to this like a much larger foundation that most people in the world have been using, which is CoralNet. And this is where everything sort of started clicking. So before 2012, many researchers were just trying to solve, like very generic coral recognition, but that wasn't what coral reef ecologists actually needed. That's not what they did on a day-to-day basis. The real breakthrough happened when they stopped inventing these new abstract tasks and just said, how can the technology make the existing point count surveys faster? That was all they were trying to do. So again, by aligning the AI output exactly with the data formats that the monitoring teams were already using, automation became like a legitimate operational tool. And that's the take-home message. That's how you help ecologists. And what was really interesting is how this software then in turn changed how things like physical diving and how data were actually collected. Right now that folks are actually aware that this AI system is in place, they've used it, they trust it, they understand it, then they actually start changing how they collect data. So the field acquisition sort of became inverted, where divers started designing their image collection specifically knowing that they could use this downstream AI, creating like huge, massive kilometer scale data sets. Which was kind of interesting. So that's another thing to keep in mind. If you produce something that is so useful, you might actually change how folks collect their data. So if you haven't seen, there's a long pause. I was letting you read it. If you're not familiar, KCD, they're a great comic strip, especially if you like STEM. Just succinctly and elegantly showcasing how hard classification was at this point in time. I think if you've played around with deep learning models and you've done image classification in a toy data set, It's like pretty trivial now. I mean, depending on your data set. But at one point in time, it was actually extremely hard. And that kind of brings us to like this next phase, where other things were happening. So like in the broader field of the computer vision, there was this huge shift. Modern deep learning was sort of coming about, and it was kicked off by networks like AlexNet, which at the time just completely dominated what's called the ImageNet competition. And I'm sure most of you guys are familiar with this, but is this breakthrough in deep learning that kind of started in 2012. There were many AI summer and winters before that, but this particular AI summer was kicked off by three main ingredients, which we've heard about: massive data sets, particularly labeled data sets, access to powerful general purpose GPUs, so NVIDIA. I think if you had bought in the stock in 2012, they had a percent increase of like 560,000. So that would have been great. And then deeper neural architectures. So these three things kind of help drive this next wave of deep learning. But what's kind of interesting is that even when deep learning was sort of exploding, like in the general fields, coral reef ecologists, or at least those who focused on computer vision, didn't immediately like adapt it and like go all in. Instead, they were there's like this interesting transitional phase where you'd actually see researchers clinging to like the older patch-based logic, but just like upgrading how they got their feature vectors. So instead of just using handcrafted features, or training a neural network from scratch, they would actually use pre-trained CNNs, so things like AlexNet, as off-the-shelf feature extractors. So they would just run an image patch through it. They would grab that feature vector, maybe calculate another one, like local binary patterns or some sort of color texture, and then kind of concatenate that together. And that would be their new feature vector. And they would use this sort of hybrid data with their existing shallow models, maybe like random forest or support vector machines. So it was like a pragmatic bridge, we'll say, between like the old way of doing things and like the new way that was like becoming more popular and sort of emerging. This paper in particular, this top one, made by Mahood, they did this the first time I saw this, and I was like, oh, that's kind of interesting. I wonder why they didn't actually just train a model or fine tune it, which at the time, it through our like bias lens, like, why wouldn't you just do that? It could just be the fact that like we didn't actually have massive data sets that were available, or maybe they couldn't be found, or access to GPUs. This paper actually underneath it was actually published in 2023, which I found was super interesting because I have not seen someone use AlexNet's features in a really long time. But I was like, this is a great graphic and it illustrates it beautifully. And now we sort of have this other shift. I'm sorry, I think I have an animation in here so you don't have to. Yeah, okay. It moves really quickly, and I was like, oh, that's driving me crazy. So we have like this other shift, moving away from like automated point counts, even though they can successfully estimate relative abundance, because of their sparsity, right? We're talking about a few 10, 100 points per image. So like, 0.001% of the entire image. Because of their sparsity, they leave gaps in the sort of spatial understanding. There's a lot of pixels that are left unlabeled. And when ecologists need to measure things like colony shape, maybe contiguous area, or these sort of complex boundary interactions, they can't really use pixels or like point annotations. Point annotations have a very specific role. They can only provide certain spatial metrics. And if you want those other metrics, you need to use different types of annotations. So it was around this time that you started moving away from these like simple cover fractions and actually started looking at like how you would actually map the benthic landscape. And it was around this time, and maybe as a result of deep learning, fully convolutional networks, things like UNet, showing major success in other fields, and wanting to adopt that and bring that to coral reef ecology. So we kind of talked about like why points as a form of annotation. Well, they're like one annotation format that can easily be used to calculate relative abundance. They sort of became the de facto because they're easy to annotate. But again, there's other types of annotations that can be used to answer different types of questions. If researchers wanted to track, for example, how an individual colony might change across time, maybe they grow, maybe they survive, maybe they split, they would actually need something like distinct polygons or instant segmentation masks. And obviously, if you want to map the entire reef, you would want to maybe provide a per pixel label for every single image or point in the point cloud or face in the mesh. So you would need something like dense semantic masks. But this is where they kind of hit a wall in here is because historically, all you really had were these point annotations. This was like the de facto form of annotation. Moving towards, polygons or dense segmentation masks would require a substantial amount of time. And again, I don't know the demographic of folks who are in this call, but if you've ever tried to annotate coral reef imagery data, or benthic data in general, it's really hard sometimes to know just from a 2D image what's going on. And that three-dimensionality, which we'll talk about later, is extremely important. So we had this problem. We had like millions of these point annotations, and they were useful for like patch-based image classification, which was done in CoralNet, but we didn't really have any dense masks, which were needed to train models like FCNs or UNets. So researchers, myself included, and Scarlett and some others, I would consider us like the wave of folks who are looking at what we call label augmentation. So there are these techniques to maybe using like superpixels to attempt to automatically propagate the expert label that was provided to all of the surrounding pixels within a contiguous group. And these, which you can see in this particular image, you've got points, and those were converted into a mask. These were sort of used as like this bridge that could be serves as training data for these deep learning algorithms. That makes sense. And the first of these techniques was actually Coral Seg. It came out in 2019. There's a backstory to that. I'll get into it later. And they sort of address this fundamental question of like, can similar looking nearby regions be grouped into superpixels and then filled in with this sparse label that I just mentioned? So this method of dense segmentation, it was something that was still done by folks, but it wasn't like a large scale form of annotation. Again, we mostly just use these point annotations. So this idea of being able to reuse other people's point annotations and automatically propagate them from an analytical perspective is really nice, because it means that all of your data that you already have can provide you with potentially pretty robust statistics that you didn't have before, and it's just an automated technique. What's even better is that you could do that, and then you can actually train your models on that new sort of augmented dense masks, and then you could then apply it to novel images that maybe you collect the next field season. So you sort of automate this technique. That's sort of the rationale for why you would want to move towards dense masks. This particular technique, which use superpixels, which are just groupings of pixels, and it's mostly weighted based off their proximity in pixel space, as well as their color and color space. More often than not, it's a lab or LAB color space. A common over-segmentation algorithm that could be used to create these superpixels is called simple linear iterative clustering, or SLIC. And it mostly just uses k-means clustering to define which pixels get grouped together in a contiguous block. And generally, it's called MSS, and then my version is fast MSS, which you'll see in a second. The idea is that you start creating superpixels, they would form, and if a labeled point existed within that superpixel, you would propagate it to all of the other pixels within that group. If there were multiple points, then you would find a way to consensus those. And more often than not, you would start with a really coarse superpixel and propagate the label outwards, and then you would go through multiple iterations from coarse to fine, so that way you would have finer detail that was captured. And that kind of showed it worked. It worked really well. Coral Seg got a couple of publications. They were very well received. Right around that same time, I was doing my master's, and I was also thinking about the same idea, completely unaware that Coral Seg existed, and I had made some pretty good progress. And I saw this publication, and I was like, darn it. But anyways, sometimes there's benefits to coming second, because what Fast MSS, which was released in 2020, it's mostly MSS, but using a slightly faster version of SLIC and a couple of other minor techniques that would increase things like MIOU and pixel accuracy. But more or less, it's fundamentally the same thing, just provides a little bit faster implementation, which helps with scalability. This is sort of, we kind of make a pivot. So we're still talking about deep learning, and one thing that like around this time we started to see is more foundational models. And this one particular paper called Coral Scop, I would say that this is one of the first times that I saw foundational models used in the coral reef ecology space. So this is not the same as doing propagating points to dense masks, although it could be. Instead, they looked at training sort of a rigid model for one specific task, and that is zero-shot segmentation to be able to do prompt-like interactions. If you're familiar with SAM, Segment Anything Model, released by Meta in 2023, it was a game changer for a lot of people who do computer vision. This is basically this is SAM, but for coral. Additionally, a major thing that they released a part of their publication was a data set called Coral Masks. It contains about 40,000 images that were scraped from the internet, and they actually created like 330,000 dense masks for this particular model to be fine-tuned on, as well as for other folks to be able to use. And a key distinction of this particular work compared to the other two was that by training this model to recognize sort of general growth forms rather than specific species like semantics, whether it's taxonomy or otherwise, you could say it generalized really well to reefs that it hadn't seen before. So they basically compared its results with SAM and found that it did, a bit better. The flip side of this, particular model, again, if the same issues with SAM, it has no ability to provide semantic labels. So no class labels, no saying it's a specific species. It's really just looking at things rather than stuff. The nice thing about it's a promptable interface. So you're able to provide prompts in the form of interactive annotation, which in some ways is actually more useful than having an algorithm attempt to provide you with a label and be a closed-sourced sort of classification algorithm. And I put CoralScope before Rain because CoralScope technically I think was published before this particular paper. So that's why I say they were the first ones that introduced foundational models into coral reef ecology. If I was wrong, I apologize. But we have Rain and colleagues who will say that they completely changed how we were looking at sparse labels. So instead of using this idea of superpixels, which again is a kind of like a low-level machine learning algorithm that just groups pixels based off color and proximity, they actually utilized foundation models like DynoV2 to sort of group reef imagery based off of this deep semantic similarity. And if you're not familiar, DynoV2 and more recently DynoV3, really cool models that are just trained on a bunch of data, and you can do some really cool stuff with them, like just tack on a really simple machine learning algorithm and train a model with it, and they work fairly well. I think the highlight of this particular paper for me, and I was reading it a little bit more recently, was the strategy for human in the loop sort of interaction. So the system, instead of asking you to blindly label random points that are scattered about the entire image, which is still the common practice that folks do in CoralNet, for example, this technique, they actually want to direct your attention to the exact areas where the model is actually most uncertain. And that's a great way to sort of maximize expert efficiency when the data is scarce, and also just minimize overall clicking. And we're going to now pivot to the sort of second branch of the story. I think I'm doing okay on time. And so up until this point, we've sort of been exclusively looking at coral reef, sort of computer vision of coral reef ecology from a 2D perspective, how researchers evolved from sort of manual point counts to dense segmentation masks, just to figure out what was growing on the reef. But you can see here in this image that there's some fundamental limitations. So like you can see in the first panel, a top-down image can maybe identify the coral and give its planar cover, but it completely flattens it, right? And it kind of ignores the real physicality of the entire reef environment. Whereas when you have a 3D model, you actually can calculate true things like volume or height and other metrics that are related to the physical architecture, which sort of highlights why the field had to pivot to the third dimension. So reefs are not flat plains, surprise, and actually a massive part of their ecological function is entirely dependent on their physical 3D shape. So in the second sort of parallel, the second parallel branch of this story is the shift from just looking at 2D images to looking at 3D models, looking at structural complexity, which happened before 3D modeling, but also photogrammetry and what's called structure from motion, which we'll get into in a second. we kind of have to understand why folks were so focused on the 3D aspect of coral reefs. And it's because of what's called, like just structural complexity, the significance that it holds. There's a really good paper called by Graham and Nash in 2013. If you're interested in ecology, I highly recommend it. To summarize what structural complexity is, and this is a direct quote from them, it's the physical architecture actively dictates how the entire ecosystem functions. And in their paper, they quantified these relationships across decades of literature, and they showed that high structural complexity provides things like essential refuge, and it has positive correlations, very strong, high positive correlations to things like biomass and abundancy. Um, and furthermore, they found that reefs that tend to have higher structural complexity also recovered significantly faster whenever there are ecological disturbances. So structural complexity is a fairly important factor when it comes to coral reef ecology. It also kind of makes sense, right? If you go scuba diving and you ask the dive master, I want to see a lot of coral, they're not going to bring you to a flat sandy bottom. There's nothing there. Instead, you need to go where there's actual physical structure. You guys know this. You're in Australia. You guys have a huge reef. You're pretty familiar with all this. So the 3D architecture sort of, you could say, underpins the ecological resilience and also serves as, it has critical services to humans as well, like shoreline protection. So the more rugose a reef is, it's going to create a lot of friction and drag for incoming waves and actually help deal with storm surge as well as flooding. So, 3D structure is extremely important. Therefore, it's as a priority to be mapped. But historically, you can imagine like calculating 3D measurements underwater was incredibly difficult, and the field often had to rely on low dimensional proxies to quantify structural complexity. And the most famous one is chain and tape method, where essentially they would just take like a chain and physically drape it across a coral reef and then like measure it. It's sort of rugose, and they would calculate a ratio, and that ratio determined if it was flat, which is one, or if it was a higher value, then it would be more rugose. You also had researchers using other methods like profile gauges, which you can see here, and I've even heard of people using like wrapping coral with like aluminum foil, or even like wax to estimate surface area. I couldn't find these images, but I know like I've seen them before, and these techniques were, they're pragmatic. They got the job done, but they obviously compressed like this rich 3D structure into a single proxy, and they were also like, pretty invasive. So to move past these sort of old like one-dimensional proxies, ecologists realized they needed to capture like true multi-dimensional geometry. If you can fully digitize a reef, then you can extract a whole suite of explicit physical metrics rather than looking at like a single metric that you calculate while you were down there. So for example, instead of calculating a single like simple chain ratio, if you had a 3D model, you can calculate true surface porosity. You can calculate things like fractal dimensions, and how they scale or how they vary at different scales, as well as some other metrics that you couldn't normally do underwater without expensive equipment. So this sort of marked a critical like conceptual shift where you're moving away from just approximating the surface, and instead you're trying to get the exact explicit geometry of the reef itself. And this is a cool couple of figures coming from, I think, 2001, where they're calculating fractal dimensions by having like a slice of a coral that was dead, and then you transition to like what was published in 2025 by Ken Dratt at CCOM, and his technique is like for calculating different spatial metrics is like the difference that you would have in 25 years is pretty cool. I get to go over this. So how do we actually build a 3D model of a coral reef? So there's different ways of doing it, but the most common is through structure for motion, or SFM. And the basic explanation, you guys are roboticists, I'm sure you are familiar with it, but it's just parallax. So if you were to hold your thumb out in front of your face and you look at it through both of your eyes, close one, your thumb appears to move because of your eyes changing, and that is parallax. That gives you disparity, which is inversely related to depth. And you can actually use that to help you calculate, where you would project points into world coordinates and create a 3D model. So you can imagine an ecologist will basically swim over the reef. They'll take hundreds of images. Usually those images are overlapping and they're coming from different angles. and then they'll use this with structure of motion to create typically a 3D point cloud, a mesh, and then sometimes an orthomosaic. And you'd actually be surprised. Structure of motion existed, or photogrammetry existed in this field of coral reef ecology well before it became popular around 2015. But they were, very specific, not for mapping entire reefscapes. But you started to see this adoption sort of post 2014, 2015. John Burns, who's in Hawaii still, had a really good publication early on, and they showed that with cheap cameras and like a decent software with a not too expensive computer, you could actually create some pretty good models. But crucially, the validation studies showed that like millimeter accuracy, while being able to document things like rugosity. The point wasn't actually to have like perfect reconstruction. It was actually trying to understand what the bias, precision, and being able to do detectable change so the field could adopt it more quickly and more reliably. And once structure from motion in this context was sort of introduced and it started looking feasible, you had other researchers that were trying to showcase how you could use it as a more serious tool and how it could be adopted on a wider scale, and folks to sort of integrate it into like their daily ecological workflow. And Renata Ferrari, I think actually somewhere in Australia. During her PhD, she had two really cool publications where they showed like early validation that off-the-shelf structure from motion was able to sort of recover this sort of complex geometry with, again, millimeter accuracy, kind of rivaling what you would get with laser scanners. So in their paper, they sort of mapped out systematically the underestimation of what surface rugosity, and they actually showed that there was an underestimation of like 8 to like 37%. And this helped give the field a sort of transparent baseline to understand and account for these inherent limits that existed within structure for motion. So again, it kind of comes back to this idea of you don't need this technology necessarily to be perfect. You just need to know, what its error rate actually is, so you can account for that whenever you're actually trying to do your analysis. So, by defining these sort of thresholds for accuracy and detectable change, they sort of shifted this idea of photogrammetry from like a neat kind of like demo that you would show people into like something that is like actively being used on a regular basis by folks, not only across labs and across different countries. And a couple of other, I think, key papers from this time. One was 2017 by Young et al. Grace Young, she worked at Google for a little bit in the Moonshot Factory. She had two really great papers, in my opinion. This is the first one. And they sort of help bridge the gap for ecologists to start adapting these 3D mapping techniques without necessarily abandoning their existing sort of historical way of doing so. So what they did is they showed that, one, using structure of motion is a valid technique, but also creating different ways of calculating the structural complexity metrics that they would be interested in, and also being able to create a bridge between the old way of doing things and the new things. So they actually created like virtual rugosity, where they would show with these 3D meshes or even a point cloud, you can drape this sort of digital chain across the surface, sort of mirroring what you would do in the field. You could actually vary whether or not it's like pixel perfect, or you could actually create the virtual chain itself, so you can actually vary the size of the chain, which would vary the structural complexity metric itself. They also introduced a couple of other techniques, code, fractal dimensions, for example, or vector dispersion was another one. I think the biggest part of their particular paper was like the impact was that you could just show that like you're able to create these sort of repeated surveys with pretty high precision and reliability, even just using GoPros and like a standard laptop. I would recommend using something other than a GoPro if you have the ability to do so, but it does show that it sort of democratized the entire workflow for folks all around the world, which is really cool. This is sort of a digression. This is a Young's second or third paper. I don't know if it was published, but in my opinion, I think it was like this is the coolest paper in this entire talk, in my opinion. So I wanted to bring it in here because it has some relevance. What they looked at doing was they actually fed raw 3D height field. So they basically took the point cloud, they created a DEM or 2.5D like raster, and they would sort of tile it into multiple pieces. and they would feed these pieces along with like labels in the form of like fish biomass for like that particular reef. And they actually trained a CNN on this elevation data and regressed it to the biomass, or like, in this case, it's just like an ecosystem function. So this is a really interesting shift because it made like zero a priori assumptions. Like they didn't tell the AI to like look specifically for any structural complexity metric like rugosity or fractal dimension. They were basically just like trying to get, in this case, a convolutional neural network to sort of understand the relationships between some structural pattern and some ecosystem function, like fish biomass. This is a really cool paper. I think it's fan. So press play. So by this point in time, which is, 2015, 2016, 2017, we knew that we could use cameras and structure from motion to create these high resolution 3D digital twins. But really, a 3D model is just eye candy until you can actually extract data from it in a way that is systematic and also, efficient and scalable. And this sort of moves us to like the next step, where instead of just creating 3D models and maps, we're actively analyzing them. So this particular video is called it's software, called Viscore. It actually comes from a fellow in my lab named Vid. And it kind of changed the game for a lot of folks who are using structure from motion data, because it allowed them to visualize just massive point clouds and sort of seamlessly navigate between a reef-wide landscape down to like a tiny coral colony. Another thing to highlight is just that the Viscore is able to scale with like significantly large data sets. It's pretty mind-boggling. In the same vein, another fellow, Clint Edwards, who's here down at Scripps, he kind of helped formalize this massive shift towards what is called like LAI, or large area imaging. So traditionally, transects, they sort of relied on random subsampling to generate statistical averages, right? You lay down a transect, you go down it, you look at the points, you create some summary statistics. Although people did do it, it wasn't super common to have researchers like revisiting the same exact spots, over and over and over. It was difficult to do so, and also like you need to put stakes out there as well. With structure from motion, you started to see teams start to shift where they would actually go back to the same exact areas, and they would sort of transition from just doing, taking images, but taking images for the purpose of structure from motion to be able to create these 3D models and orthomosaics. So this particular image is showing an orthomosaic from time point 0, time point 1, and actually measuring the difference, the change in between those two. So this allows for longitudinal demography, essentially allowing ecologists to track the history of individual coral colonies. So, their growth, their shrinking, their dying, their fragmenting, survivorship across time. And these were techniques that were used by 100 Island Challenge and Mission Iconic Reefs. But to be able to do this, you had to create certain types of annotations, because again, those random point counts couldn't be used to track individuals. You need polygons to delineate the individual and to be able to track across time. And this is also when Tag Lab also became a thing and also extremely important. You can kind of think of like if CoralNet was the first major hinge for point counts, Tag Lab is sort of the equivalent for dense like area-based annotations, specifically for orthomosaics. And what made Tag Lab historically significant, again, I would say it's not the AI. It's like the fundamental philosophy. Like they didn't try to erase humans from this entire process. They didn't try to automate everything. Instead, they just treated humans as a way to correct the annotations that were created by the AI. So they were an integral part of the system, which, if you want people to adopt your techniques, usually you don't want to replace them. So keeping humans in the loop is fairly important, in my opinion. I think before Tag Lab, if folks wanted to do demography, they would often use sort of general purpose image annotation software, I think like Photoshop. But with Tag Lab, folks really started to move towards this. And this is, I think, worth said. So large area imaging sort of like gave us this incredible spatial context, but it also introduced like this highly ironic technical problem, where even though you have these orthomosaics that give you like this large area, the entire area of the reef that you're looking at, orthomosaics still have issues with resolution. they're not always particularly high, and they also contain stitching artifacts. So oftentimes, folks who are looking at orthomosaics can't actually identify the species that they're looking at because the orthomosaic resolution is too low. So, developing a system, this is a tool inside of this core called VPI that would allow folks to actually look at like where a point is on the 3D mesh or the orthomosaic and see the high resolution source imagery that was used to create the 3D model. This is kind of like a weird thing, but it's essential to be able to do taxonomical identification. I'm going to skip this. Yeah, this is sort of the last pivot, actually. And this is where we kind of like merge these two stories together. So you had ecologists who like now, more or less have the ability to create these 2D semantic maps for their particular images, but that they necessarily have it associated with the 3D models that they were now creating. So you could do structure for motion, you can calculate structural complexity of the entire 3D model, but you wouldn't be able to say specifically that this particular taxon or this class category is contributing, this amount to rugosity or fractal dimensions. You're just looking at the reef as a whole. So being able to merge these two ideas of semantics or class category and the three-dimensionality is kind of like where we're at right now, I would say. The first was actually made by Hopkinson. What they actually did, it's kind of cool. They basically looked at every single face within the mesh, and they would drop a point, or they would use the centermost point on a face of a mesh, and then unproject that back to all of the cameras who had it in view. They would then extract a fixed patch size from all of those different views, run a CNN on each of those patches, and then get like a list of different classification predictions, and then do a consensus. And then that would be the final label for that single face in the mesh. And you could do this, where for all of the faces in all of the mesh. And it's surprisingly like good and accurate because you have all of these different perspectives, but you can imagine it's a very time-consuming way of doing this because you're looking at, potentially, tens of millions of faces, and for each face you're looking at, tens, maybe 20s of images. The second approach, this is one of mine, was very similar in concept, but doing the opposite direction. So instead of looking at it on a face or unprojecting it to the images, what you actually do is you start out with your source images and you perform semantic segmentation on them. And then you basically hot swap the images with these semantic masks you can see here, and you reutilize the camera projection matrices that you created during the structure for motion process. Because you can imagine SFM, you're creating the mesh, the 3D point cloud, you're using the RGB color component values, and you're projecting them to create, the colored mesh. You can do the same thing with labels as well. And this is a way of doing so. And again, you actually take advantage of the fact that you have multiple views for each individual face of the mesh or point in the point cloud. So you get a consensus and you get fairly good results. So this idea of multi-view actually naturally helps get slightly better accuracies. And then this is kind of like where I would say we end, at least in this sort of evolution. This was one that was done by Jonathan Sanders. So the previous two showed how you could project 2D AI predictions onto the 3D model, but there is still like this massive catch, right? The underlying photogrammetry step to build those 3D models took hours or sometimes days of computing. So this is a really cool paper. If you haven't checked it out, I highly recommend it. They've been making a lot of updates to their repository recently, including adding this GUI, as you can see here. It's called Deep Reef Map, where instead of like this old two-step process of building the model and then doing AI and then sort of projecting it, they just have like a single pipeline that both reconstructs the 3D geometry on the fly and then actually creates semantic masks and then projects them onto the point cloud as it's being made. So for an example, a diver can swim like 100-meter transect with like a GoPro, and in 5 minutes, they can upload it into this application, and then maybe another 5 minutes they would actually have fully segmented results. I think this particular model is still like a closed source model, so it's only able to predict on the things that it's seen. But the idea of integrating these two into an application that's easy for people to use is definitely a step in the right direction. So, what does that mean for the future of reef ecology? I would say that we've kind of like officially entered into this era of like the semantic digital twin. I'm still wrapping my head around the idea of a digital twin. I've yet to see like what I think is convincingly a digital twin. Conceptually, I understand it, but I don't, in core Reef ecology and otherwise. But I would say that we're like no longer limited to like flat 2D dimensional approximations, right? So geometry and species identification can now be extracted together as a single sort of integrated product. And that is pretty cool because it solves like our historical bottlenecks of turning 3D mapping from a sort of slow visual novelty into a rapid daily monitoring tool, assuming folks adopt these techniques, which takes time, and it's understandable. I'd say that ultimately it shifts the entire ecological sort of baseline from simple percent coverage, which was done like a while ago, to measuring like true species-specific volume and structure resilience. Again, being able to look at a 3D structure and knowing how each class category contributes to it is extremely cool. And with that, I have a couple of future directions. I'm not going to spend too much time on it, but these are areas that are kind of on my mind on a regular basis. In particular, Gaussian splatting. Neural radiance fields are really cool. If they make a comeback, we'll see what happens. But Gaussian splatting is an interesting technique. I think a lot of you folks, if you're doing with robotics, you probably spend more time working with on the edge compute than I do. But I know there's a fair number of people like Flyfish Technology who this is sort of their bread and butter. And also looking at sort of ecological foundational models. So there's a lot of foundational models that are coming out that are, specific to like satellite imagery, for example. Having something like that for underwater vision, I think could be kind of a cool thing that someone could look into. And Gaussian splatting, if you're familiar with it, kind of like point clouds with an additional Gaussian on top of it. Points in a point cloud have no volume. So if you were to, splat it against your image plane, maybe it'll fill in a pixel, maybe it'll fill in a couple of pixels, but more often than not, it's less than 1 pixel. So you end up with a sparse sort of depth map. Gaussian can help kind of fill that issue where it is an explicit form of geometry, but that Gaussian that is trained can kind of help fill in that area. So it's a nice kind of in between the point cloud and the mesh. And I think a lot of folks are really interested in how it appears. So this is something I took from Sergey. He's a CEO of Wildflow.ai. If you haven't seen his website, it's really cool. Recommend checking it out. And he's very much pushing for Gaussian splatting. And I think it does have like some opportunity to solve some of the problems that exist, in particular working with orthomosaics, where it's really hard to see what the species is in the orthomosaic, but then you have these additional side views to help you with identification. And, just wrap up, 3 kind of big shifts. Ground truth became statistical. Our annotation unit moved from single points to continuous surfaces, and structural complexity sort of evolved from simple proxies to explicit geometry. But the deepest transition is the capturing of underwater images. Like that's no longer a bottleneck. Now it's all about data infrastructure and data compute and storage. And I would say that like the future of computer vision isn't necessarily about inventing one magical new algorithm, unless you can create a really, really cool one. In reality, it's like building shared standards, making sure that data is not siloed, that everyone has access to data labels and the ability to create their own machine learning models. I think is like an important thing to sort of focus on. And I think with that, I think that's pretty much it. So kind of.
Thanks so much, Jordan. That was absolutely fantastic, really interesting, and a great overview of the field. We do need to wrap up the session pretty quickly, so I'm just going to do one question, and then, of course, you can reach out to Jordan one-on-one if you have further questions or want to chat more. So is there one question in the room that we can ask? Matt, did you have one? No? Sorry, somebody else?
No, okay.
I've got one, if not. I thought it was really interesting, that paper that you presented that went directly from the 3D model to the fish biomass. That's one that I hadn't seen before. I'm just wondering, why do you think that kind of idea didn't take off massively? Do you think it's because it's a little bit abstract, or it does take away those intermediate predictors that are easy to understand?
Honestly, I have no idea. I know I can reach out to Grace, on LinkedIn and ask her. I think it's like a really great idea. If I have to be sort of like lame and say this, I think it was before its time. I know it's like a really like nerdy answer, but like I have no idea. Because I do think that even today, it's something that if someone wanted to build on top of and use that as a reference, I think that's like sort of prime real estate to move into because it's a really interesting idea, and I haven't really seen a lot of other publications that look at that, and I think it has direct ties into folks who are developing artificial reefs. So if you're someone who's interested in fabrication and like 3D printing, the ability to have AI intertwined and understand how the physical structure of a reef and how it positively corresponds to certain ecosystem functions, you might be able to use that as like a way of creating more specific structural designs rather than just, creating something and putting it in the ocean and hoping that it works. Instead, you have a more systematic way of doing it. But yeah, I'll have to ask Grace. Yeah.
Awesome. We might leave it there. Thank you so much. Can everyone join me in thanking Jordan one more time?